Live in 5, 4, 3, 2, 1. We're live.
Hi, this is David Greenberg coming to you with episode 27 of the Machine Learning Seminar at Helmholtz Centrum Herion. And we have a really nice paper today. It's going to be presented by Demir, a master's student in our group. It's about applying the physics-informed neural networks framework to the shallow water equations. And what I really like about this paper is that it goes somewhat deep, both in the kind of thinking and analysis you do for machine learning. You know, what kind of networks do we build? What loss functions do we use? How do we do our optimization? Without losing track of the logic of earth science and how do we evaluate our solution and what does it mean? And I think they do a nice job kind of combining these two disciplines. And this is really the kind of paper we should be covering. So with that, I will turn over to you, Kubi.
Yeah, thank you. Thank you for the nice introduction. Hello, everyone, and thanks for joining the machine learning seminar. So this was already a good introduction to the paper. I share this opinion. But as this is already the third paper about physics-informed neural networks, you might ask, why is this now important? Why should we look at the shallow water equations as an example? And the reason is, and I'm also a bit rephrasing the motivation that was shown in the paper, is that finally, at some point, we want to apply this concept of physics-informed neural networks to an actual dynamical model, right? So we want to replace some dynamical core of some model, let's say for numerical weather prediction, and it should rely completely on, for example, a neural network based on physics-informed neural networks. However, there are also requirements that need to be met in order to make this possible. And the first examples are just, for example, physical conservation of quantities as mass and energy, which is not implied by physics neural networks implicitly. And also representation of, for example, balance flow or other dynamics adjustment to balance flow, and also problems like grid printing. But at this point, for example, physics-informed neural networks have an advantage, which is that they are not grid-based. They're basically, and we can choose points for our training wherever we want. And also there are already ideas on how to put hard constraints on the conservation of, for example, mass and energy to tackle these, but more about this later. But just upfront, for example, about the paper, they argue that already there's a good point for this approach, which is that the cost of the training is comparable to the total cost of data assimilation and numerical integration of numerical weather for prediction models, which if the cost doesn't increase significantly with more complexity, it would be applicable in the same way. Yeah, so before we actually go into the paper, I want to give a recap on the concept of physics-informed neural networks. And I will start this by motivating why it might be a good idea to apply cost of the training, the PINs, to solving partial differential equations, comparing it to numerical integration and also other machine learning approaches. Then I'll explain how the concept works, showing an example from the original paper where it was published. And then I'll show two more applications, which were previously shown in the episodes 1 and 25. And then I'll compare them conceptually. And then finally, I will look into the paper. First, introduce the shallow water equations themselves in spherical coordinates. Then we'll look into the different approaches that were used in this paper to tackle this problem. And then I'll show finally the results they got. So let's look into the different ways of solving partial differential equations. Up to now, still numerical integration, especially in fluid dynamics, is the go-to approach or the state-of-the-art approach to solve partial differential equations. And the way it works is that we start from some initial state, x0, which is our initial condition, and then we integrate the partial differential equations in discrete time steps to integrate to the time step we want. So we have a spatially and temporal discrete representation of the solution. And this has been tested for several decades and is also accurate, and there's diverse methods for different problems where we can solve this different problems accurately. However, with the discretization and the resolution of different processes at different scales, we'll get a high computational cost, and at some point the computational or the amount of computation we can do is limited, and therefore in some examples it was already tried to replace these with machine learning approaches such as deep learning. And there the classical approach would be that instead of numerically integrating, the neural network is trained on simulation data, such that it learns how to make a state update in the same way, so that we have some initial condition, and the network is applied iteratively, so that it makes state updates up to the point of where we want to integrate to. And for this, we only need the training data to train the network how to do the state update. And then we need an initial condition as an input from where to make the state update. And as I said before, the main reason for this is to increase efficiency. But compared to the PINS approach is also that you can apply it to any initial condition. But I'll come back to this later. Yeah, but they share problems as the discretization and the ability to generalize, because we're just training it on the numerical integrations, right? We are not actually using the physical equations, which actually describe the change of time of our variables. So this is where the motivation comes from, to introduce the partial differential equations to the training. And this is how physics-informed neural networks were actually invented. So the idea was that in our training, in our loss function that we minimize, we want to include the partial differential equations, and thereby learn the complete solution continuously in space and time of the partial differential equations. And for that, we use loss terms that consider the partial differential equations, the initial conditions, and the boundary conditions. And the advantage is that we don't rely on a discretization. We don't need training data from simulations, for which we usually need a lot, which is not always given. And also we use the physical laws that are already well known and that are used in numerical integration. But a disadvantage of this is that we need to specify the initial and boundary conditions, so that we can't just solve any for any initial condition for a specific equation, but we're bound to this. And also, if we then have to always retrain the network, this would again be relatively computationally expensive, but this I will discuss later. So let's now look at the original paper where the physics-informed neural networks was first published. And the idea is, which I show now for the Burgess equation, that you can choose some form of the equation that is 0, and then you can represent all these variables in there. So this basically consists of derivatives of the function in space and time, and the function itself, and some sum of products of this. So this you can calculate for any function that is sufficiently differentiable. And this could, for example, also be our neural network. So if your neural network is some function u, and is dependent on t and x, we can compute this this form, which is supposed to be 0, at a finite number of places in a domain. And then if we minimize them, and we also consider the initial and boundary conditions, which are shown by these x's here, then if all these terms are 0, then we by definition get a solution to the partial differential equations. So just because I didn't mention this, so this is the solution to the Burgess equation over space and time. And on the boundaries here, you see the sampling points for the boundary conditions, and here for the initial conditions. And the ones for the partial differential equation loss term are not shown, but they would be spread over this here. And this paper has shown that these networks are indeed capable of representing at least solving at least simple equations. And in a follow-up paper, the authors applied this to more realistic applications with a slightly new concept. So in this case, instead of using data on the initial and boundary conditions, we actually have some data inside the domain, which is in this case shown in these figures B. So this is the reference. So for this two-dimensional space, we have some snapshots in time, so they're only discrete, of some tracer. And what the network actually does in this case is, by considering the physical laws and the data of this tracer, is reconstructing the continuous field over the whole time domain, not only of this tracer, but also of the pressure field and of the velocity field, which is shown below here in the streamlines. It's basically the horizontal field at a given time. So yeah, and so the difference is that we here, instead of just solving an equation, also do some kind of data assimilation task, which is, I think, very interesting, that there's a combination of solving the equation and data assimilation for this variable where we have only discrete given data. And in the or two episodes ago, we looked at a very different approach, which isn't directly a physics-informed neural network, but it's a slightly different approach. However, we still use this physics-informed loss function, which describes how well the network meets the equation, which in this case is the incompressible Navier-Stokes equation. Then also the incompressibility, and also some terms describing the initial, oh no, sorry. So basically the terms, the incompressibility, the Navier-Stokes equation, and the boundary conditions. But the difference here is that we don't try to get a continuous solution of the space and time, but we actually here do a time update. So this is some kind of hybrid between for example, the standard machine learning approach, for example, emulators where you do a time update, and the physics-informed neural networks where you have this loss function. And one thing that's also similar to the other machine learning approaches or numerical integration is that they actually use a discrete grid for representing the variables, and also specifically one that you might use in a fluid dynamics application. Because here all variables are not at the same place. That is very convenient for determining the discrete representation of the derivatives, because the variables or the difference that you're computing is always, or the value that you're, where you are computing the difference is always centered by the two values that determine the difference. So for example, if we want to compute this value, that's determined by the difference of these two values, and it's centered, so it's a better representation than, for example, having a step from here to here. And this also goes for the variables like pressure and sea level, which are centered by the velocities, which makes the description of, for example, advection processes much easier. And there are two more interesting points. So one is that they actually don't use just a fully connected network as in the previous examples, but they use this unit structure, which also has the capability of recognizing some structures. And additionally, they're also using features which describe the domain and also the boundary conditions. At the boundaries of the domain.
Can I just quickly ask, the UNet they're using is a convolutional network, right?
Yes, exactly. So they have, down here, they have convolutions, but they also have direct connections between the layers before doing the convolutions and the final layer. So yeah, so this is basically the network goes forward. Yeah, but the last thing is, which is actually also an interesting physical concept, is that we want the velocity field to be incompressible, which is described by this equation. But what we can also do is we can say we can do a Helmholtz decomposition, which you can basically do for any vector, so that you split the vector into a gradient of some scalar and a curl of some other vector. And if your vector is indeed, or if the velocity is incompressible, then you only have this term, because the divergence of a curl is always 0, and this term could potentially be non-zero. So what they actually do is, instead of directly predicting the velocity field, they they make a time step for the potential of the velocity field, and then compute the velocity field by taking the curl, which I think is a very neat solution to avoid having too many terms, because what we will see later too is that it is also difficult to optimize a problem where you have too many different terms that you want to minimize, because then the gradients for this might conflict. Okay, and what we can see is for this example that they show for different Rayleigh numbers the transition from laminar flow to more turbulent flow, and show these physical effects. And what's very neat is that they generalize without retraining for different geometries, which you can see here, for example, and still get realistic solutions. Yeah, so summing up, we had these two typical physics-informed neural networks approaches, where we had two slightly different approaches in the sense that we once take the initial and boundary conditions, and in the other case, we take this tracer data to actually solve the equations. And as this was the first approach, so generally first the aim was to not have to be bound to data, and also somehow use the equations. And here they somehow expanded the problem and probably tried to apply this to some more realistic problems, and found that this way of doing is probably the best to also maintain a good accuracy. But in this third approach, they actually mainly aimed at trying to generalize the model very well, because they saw that in these other approaches, for example, that they are bound to initial conditions and also for a certain domain. So you're solving a very specific problem, but they try to find a way to be able to attack different or a very general problem, and therefore they used all these tools that I mentioned before. Yeah. So now, having made a recap about physics-informed neural networks and similar approaches, so what we are going to see now in the Shell-Water equations paper is similar to the first approach. So we're also going to include the partial differential equations and the initial conditions, but there will be a difference about the boundary conditions, but we'll see that later. So they somehow implicitly define this. And now we go to the paper. So as we said before, this is applying physics-informed neural networks to the Shell-Water equations. Was just published this April. And yeah, so first, for introducing the equations, the Shell-Water equations are three partial differential equations. They are derived from the Navier-Stokes equations, and the approximations are ones that is a hydrostatic approximation. So that means that the horizontal scales are much bigger than the vertical scales. And the second is that we have constant density. And then these three equations, so the horizontal momentum equations and the continuity equation, fully describe the system. And instead of a mass conservation, we now have a conservation of water volume, or in this case, this describes the sea level elevation, which implicitly describes the volume. And to briefly explain the different terms, so for the U and V equation, these are always similar. So the first two terms for both are the momentum advection, so momentum that is moved by the velocity field itself. Then we have an influence of the Earth's rotation by the Coriolis force. Because we are not in spherical coordinates, we also have some curvature terms in addition to the ones that we usually would have. And because of gravity, we have a pressure gradient term that balances its gravity. In the equation for the sea level elevation, all these terms describe somehow the advection of the water volume. There are different interpretations for these terms, but it's not so important for the interpretation right now. Yeah, so now let's look at the different approaches they choose to tackling this problem. And while trying to solve this most accurately, there are different sources of errors that they might face, and they have different approaches for each. So as a first problem, we might assume that if we minimize our loss term, that we might not necessarily, depending on, for example, the learning rate, the optimizer we choose, and such things, we might not actually find the global optimum, but only some local optimum, so that we already have some error because we don't find the actual optimum. Then another term is, just to explain this, so the y-axis is basically the loss, and the x-axis is the parameters of the network. And here you are seeing the loss function for two different networks. So now if you have some network that has a relatively simple structure, it's not very deep or wide, and doesn't have many parameters, you might not be able to actually get a very low loss. So that by just having a more complex structure of the network, you might already be able to have a lower loss and a more accurate solution. And then the third possible problem is that you might not have enough collocation points. So these are the points where you try to minimize the loss function. And if you don't have enough, you might end up having a function that fits the points that you have, which are in the coarse case now are these small x's. So if you only have a few points, you might have, and you have a big network, you might have the problem that it overfits and doesn't actually fit the function, but just fits the solution well at these few points. So then you will see when you add more points to it, which are represented here by the blue circles, that you then end up having a much more accurate solution just because you consider more points and the network isn't overfitting. So for each of these issues, they have different approaches to work around them. And for the approximation, so this is the capability of the network, and estimation, which is mostly focused on the collocation points. They once do a sensitivity study where they test different network architectures to see how they influence it, and also the number of collocation points, and see when they reach the lowest loss, which we'll see later. And then another approach, which is because this is a relatively normal approach that you would do a hyperparameter study, but a more interesting approach is that they try and split the time interval into different models so that they don't have just one model, but several models, which might make the models more capable of representing the function that they want to approximate. And then one other approach for tackling the problem of having different magnitudes in the equation, for example, for the sea level and the velocities, is non-dimensionalization, which is also very typical for numerical approaches to for example, fluid dynamics. It's very normal to also characterize the flow by different non-dimensional parameters. And so the last thing, as I mentioned before, if you have different parts of your loss term that you want to minimize, you might encounter the problem that these different gradients don't or agree in the way that they don't point in the right direction, in the same direction to change the parameter, but actually they conflict somehow. And therefore, there was some paper trying to solve this by projecting the gradients, which I will explain later. And one other thing that is done in this paper is they explicitly define set the boundary conditions so that they don't have to actually minimize an additional term for in the loss that just focuses on the boundary conditions, but only have to focus on the initial conditions and the partial differential equations. So now about the non-dimensionalization. So for applying non-dimensionalization, you have to choose scales for your variables, and so your space variables. So for example, in the horizontal, so for x and y, they chose the radius of the Earth, which is a here, and then they chose a time scale, which is basically 1 day. And based on these, they have also a scale for the velocities, because this is basically distance per time. So this is implicitly given. And in the vertical, they actually base it on gravity, the horizontal space, the time scale, and also some additional factor to adjust this. Yeah, and as you can see, these are basically the same equations, just that now every variable is represented by a non-dimensional version of it. So you basically take the variable and divide it by the respective scales to non-dimensionalize it. And the same you also have to do for the derivatives and the parameters to get this. And what you then get is that instead of having a variety of different scales, which might be a problem for the optimization, then you get relatively similar reference scales so that everything in Optimus is on the order of 1, so that you have the same order, and it is easy for your optimizer to optimize all terms that you include. Because, for example, if you have some gradient tolerance, and then your h has a much higher value or general magnitude than your velocities, then if you have the same gradient value, that might be as a relative error much higher for the velocities because they're generally smaller. Okay, and as I mentioned before, they also have used this method to not have to explicitly make the network obey the boundary conditions, and they do this in a smart way in which they make the first layer of the network a coordinate transformation. So the input to the network is actually time and then the longitude and latitude. And they represent it then in the next layer in Cartesian coordinates. So I have shown the space of latitude and longitude here. So they project this on a the surface of a three-dimensional sphere. And on the sphere, then you explicitly already have the boundary conditions given because the transformation itself is periodic in the boundary. So it's 2π periodic in both directions, such that even if you input a value that is the same plus 2π, then you will have the same actual input to the network. And on this spherical surface, you don't have any boundaries in that sense. Yeah, and another approach they choose that was presented in Tianhe Yu et al. Is that if you have different parts of your loss function, which is a multitask objective, so you try to minimize two different terms, then you might have the problem that these terms, which are here symbolized by these two arrows, are not pointing in the same direction, and also might have very different magnitudes. And the way they propose this could be solved is by projecting each of these gradients onto the normal plane of the other one. So they show this in these two following figures. So the normal plane of this GJ would be here, and then they would project the GI on this plane. And in the following figure, they show that projecting the GJ on this plane horizontal to GI. And then you'll end up having some gradients, and they are not the actual gradients. So this is just an example where they are not conflicting anymore. And in this way, you might end up not getting stuck in a minimum. And to illustrate this, they show this in this bottom figure, where you here have shown the multitask objective, which is also shown here. 1 second. So yeah, where the first task is this, and basically these darker spots are where the loss function is the smallest. And you see here for the second task, there's the minimum basically here. And the problem is if you start at a point which they choose to be here, if you look at the second task, you don't have a very strong objective to go towards this direction, although your minimum for both tasks would be here. But the objective to go to this direction from here is much, much higher. So this is represented by these two arrows. So the red arrow is the first task, the objective of the first task, and the blue arrow is the one of the second task. And this is actually logarithmically shown. So by orders of magnitude, this first task is much more prone to be, or will reduce your loss initially much more than this one. So this is why the optimizers might land in this local minimum, but would never reach the minimum for both tasks. And what you might end up with is a compromise solution where, for example, let's say your initial conditions are met, but your partial differential equations term is not yet very small. And using this projection approach in this example, they show that then the optimizer actually finds the global minimum more easily. And even more interesting is that they give a small mathematical proof for some conditions that the loss with the projected gradients after an update will be smaller than the loss with a normal update without the projection. And the conditions for this are, first, that the gradients are sufficiently conflicting, which is obvious because if they wouldn't be conflicting, you would probably afterwards have them be more conflicting. So you want them to be sufficiently pointing towards different directions. Then also, as we've seen before, it's most problematic for the optimizer to find the minimum if there's high curvature like here, because then it's going to overestimate the importance of the one gradient versus the other, which will seem not enough important in that sense. And another factor is the step size or learning rate, which if you have a high learning rate, you're more prone to actually get stuck in the local minimum, because you're even more overestimating the importance of the one gradient. Yeah, so the idea is that if you use this this projection in these cases, that then you end up actually minimizing all your parts of the loss function, and then actually get an accurate solution. Okay, and now we are getting to the last tool that they are using, which also isn't completely new. So this kind of domain splitting has at least also been used in numerical methods, or I think also other machine learning methods. But in the way they do it is also very interesting. And yeah, just briefly explain. So they basically fix a number of samples that they choose in the complete domain. Also, for example, for just one network. So here we have, so one slice here is basically one solution or one space at one time, and this axis represents the time evolution. So these are all the samples that they take for evaluating the loss term for the differential equations. And if they train one network to predict this time evolution from the initial condition over the whole domain, they use this whole number of collocation points. But what they do now, if they split this domain and evaluate each domain with one network, is that for the training, they always only use the points that are within the domain, so that they then hope to save computational costs, because the network will converge faster, and also you save costs by just using the split of the points. Okay, but how does this work? So they don't compute all these or optimize all these networks at once, but they do them one after each other, because they first use the initial condition and the collocation points in the first domain to optimize the first network. Then they use the output, so basically this blue plane here, the second blue plane, as the new initial condition for the next network, and then they also use the parameters of the old network for the new one, such that they hope to converge faster. And they do this n times for n domain splits, and also have n models. So in this case, 3 models. And yeah, so they optimize 3 models and repeat this 3 times. And then, as I said, the hope is that because you're for each epoch you're using less collocation points, that the network will converge faster. And now we will see results for this case. So for this paper, they actually use a number of test cases that were for the shallow water equations that were proposed by another paper, basically for testing numerical methods. And in this test case, first we can see here the spatial domain. So it's latitude and longitude. And on the left-hand side, on the top, you see the initial condition, which is basically an elevation here, which is a cosine bell. And what they assume is that they don't solve the full shallow water equations, but instead they ignore the velocity parts of the equations for the velocities and set a constant velocity field, and then only solve a linear advection equation for the sea level elevation. And in this case, this cosine bell would just be advected and would basically be advected once around the equator, so that after or at the final stage, they would expect it to be exactly at the same point. So that is why they here show the initial condition and then the difference to the initial state, because this basically is the error they see at the final stage, so at the last time point, which is if they use just one model and train it for 18,000 epochs, still very high. So it's basically, if you look at the difference, this is basically almost the full cosine bell, and it's almost completely dissipated. So the idea was then that probably the network doesn't manage to connect the initial condition to the time evolution. And that's why they try to use multiple networks. And this you can see very well here in the learning curve. So this on each of these, the losses on the y-axis and the number of epochs is on the x-axis. So instead of just training one network until it hopefully converges, they use half of the epochs to train one model for half of the time domain, and then initialize the second network with the same parameters and use the output here as the new initial condition, and then also train the second network. And what they see is that then they get a very significant reduction in the error of the output. And instead of a completely dissipated solution, they actually get a solution which has about 7% error instead. And then if they keep increasing the number of models, which they do up to 4 models, they first also get, again, a decrease in the error. So it slightly decreases, note only less than a factor of 2, maybe 0.6. However, in addition, they also save time because they have the same number of epochs, but for each epoch, again, less collocation points. And thereby they save a lot of time. So they get a more accurate solution that is less expensive computationally. And they also test this for the same problem, but in this case, the constant wind is not along the equator, but it's towards the poles, so that this cosine bell is advected towards the pole, and then what also goes once around the globe. So why would you test this? The idea is that usually discretized models have a big problem with resolving dynamics at the poles, because there the coordinates have a singularity because they all go together, and the distance between the longitudes becomes very small. However, this model managed to still also get a very good solution. And here again, they use 4 models. So to compare to this, they get a very comparable solution even for this case. So now for the second test case, and this is the first one where they actually use the full shallow water equations. Now they integrate over 5 days, and in this case only use one model. And so in this is a geostrophic flow that is not, so it's not completely constant, but after a certain time frame it repeats. And what you can see here is again the difference of the final compared to the initial state, because at some point the system state basically repeats, and they take this time after 5 days and compare to the initial state. And you can see the errors here for the sea level elevation and the 2 velocity components now. And just as a reference, here the magnitudes differ. So here they already calculate again the dimensional variables from the dimensionless variables. And again, they managed to solve this very accurately. And for this case, they actually do a hyperparameter study to check whether the architecture of the neural network or the number of collocation points that they use makes a big difference in the optimization. So each table shows horizontally an increase in the number of collocation points. So here it's just 1,000 collocation points for the internal domain and 100 for the initial condition. And then the same here, so 10,000, 1,000, and so on. So 100,000 here even, and 10,000 for the initial conditions. And vertically, you see that here is so the linear 2 norm for for the relative error of h and for v, and then also the maximum error, which are described by these terms. But I want to go into detail about this. But what you can see in all these cases is that because the network architecture increases for these, so here we have 4 layers with 20 neurons, 6 with 60 neurons, and here 8 with 80 neurons. But the difference in the relative error actually doesn't vary as much between the architectures, but way more with the collocation points. So if we use 100,000 collocation points in the domain and 10,000 for the initial conditions, we already get something on the order of 10 to the minus 4. But if we use a very, more complex model, which is way bigger, but don't use as many collocation points, then we don't get something comparable. The solution still gets better. So this is still, again, a factor of 2.5. But the more essential factor is definitely the number of collocation points, which means maybe if you don't use enough, it might be overfitting. And it's necessary to take a high number of points. However, so they don't use all of these points every single training step, but this is the full batch, and they always do a small batch, which is on the order of this. So they always use a mini batch with 1,000 points in the domain and 100 for the initial conditions. Yeah, and basically the same as I said before also accounts for the velocity fields. Again, you see that it makes a bigger difference to increase the number of collocation points than to have a bigger network. And now I'll show two more different cases that they look at. The first is one where they have a constant zonal flow, but at this point they have an isolated mountain. And because of this mountain, the model should exhibit or show Lie waves that you can see develop in the later frames. So in the beginning, there's no waves, but then because of this mountain in the east of the mountain, in both hemispheres, you see these Lie waves forming. And this is one of the properties that they also should behave so that in order to reproduce the physical, so the properties of the solution, but also they look at the conservation of different variables, which is here the mass, the energy, and potential entropy. So this is kind of an integral over the square of the, it's not so important. So what we see anyways for all the variables is that they are not completely conserved, but they are relatively small, but for replacing a numerical model, we want them to be completely zero, or at least very much smaller than this. And we also see the same for the second example with the Rossby-Haurwitz waves, where we have this wave structure that is advected eastwards. And again, they can reproduce these kinds of waves, but we have the problem that the quantities are not completely conserved. And this is also a major thing that they mentioned in the conclusion, that this is one thing that they want to attack next, to somehow have a hard constraint on the conservation laws. Yeah, so to conclude all this, this paper has shown a few different aspects how the training can be improved for physics-informed networks, which are interesting. And also go along the lines of the physical approaches, as David said in the beginning. And especially with the splitting of the time domain, they seem to find very good solutions. We don't have a comparison for the conflicting gradients or non-dimensionalization without using them, but at least it seems like they find good solutions using these approaches. And yeah, it's also interesting to see that it's in this case that it's way more important to have enough collocation points than a more complex network. Yeah, and to conclude about the capabilities of the approach. So what they managed to do is they reproduce certain wave phenomena, and they also find agreement between their solutions and the numerical solutions. And for the first few examples, they also showed that the errors were relatively low. But the main point is also that they say that for these, for reproducing these wave phenomena, they also don't need, they need way less collocation points than a normal numerical approach would need in collocation points. And that might also be a reason why they can't completely conserve all these quantities, because yeah, they are still missing some of the domain. Yeah, and thanks for your attention. And now I'm open to questions and a discussion.
Thanks a lot, Kubi. That was a great presentation. You covered a lot of ground, and I think really clearly. Yeah, so who has questions, just jump in or maybe write in the chat. I don't know if someone is looking at the YouTube chat as well. Occasionally we get a question there as well. So while we're waiting for the first question, let me ask a question. I struggled a little bit to understand the graphs in figure 5 in the sense that, you know, we're seeing, this is where you have the, these,
Sorry, which one is it? This
yeah,
one?
the steady state solutions, right? So in the paper, we're seeing, there we go, right? So we're seeing these errors, and I would just have to do the math and calculate, you know, I don't really have a sense of how big these errors are compared to the signals that, I mean, obviously for the case of U and V, well, we have used the max velocity is, let's see, supposed to go around the world in 12 days from the text below equation 6. But I'm not sure what the units are. I just don't have a sense of, are these big or small errors? Likewise for the height, I'm not quite sure how big the variations, you know, because the initial height, which is a steady state, is varying over latitude. It's decreasing with you know, I'm sorry, it's increasing with the sine, decreasing with the sine squared of latitude, it seems, in equation 6 in the paper. So how big are these errors compared to the signals we're trying to capture?
Yeah, so far, I think for the sea level elevation, it's between the 1,000 and 3,000. So even if it's 1,000, this is already still 0.1 error. So
I see, that's very good then.
Yeah, and I think for the velocity, it's a bit more hard to say because even if it's between 0 and 40, it's unclear where or how much of the domain is actually much higher than 0. So there, I think the same would have been good to see the actual solution.
Yeah, okay, but overall, it's pretty good, it seems.
Mm-hmm.
Any more questions from the chat? Something I think would have been nice to see more of is quantitative comparison to numerical solvers.
Yes, I agree. I think that was a bit sparse, especially for the later examples. Yeah, so it would be interesting also how low, for example, the conservation of these sources, because if you have some numerical error, you will also have some kind of loss of these variables. So the question is how high can it be? And also how would it be locally compared to the whole domain?
Right. Anyone else have a question? Okay, let me ask one more question. I see a microphone on, but I'm not hearing anything. One of the advantages they claim is that they don't have to deal with singularities in the same way as numerical solvers. So they see this really nice bump when it goes south to north. It just passes right over the equator, spreads out in latitude longitude coordinates, and this may be something difficult for numerical solvers that struggle with the singularity of the poles. But what I'm not getting is, if you look at their overall statement of the shallow water equations, I think you had a slide on this, Kubi.
Sorry, I thought you meant this part again, but
you know, that was correct. That was the one I mentioned. But if you go back to where they actually show the equations, right?
Oh, okay, yeah.
The formula they use, right? There are all these terms where they divide by the cosine of latitude. So this also has a singularity. So what happens to this function, this set of equations, and what happens to their objective functions as we get close to the poles? We end up dividing by some very small numbers, right?
Yeah, that's true. I'm not sure how they handle this. Maybe I have some kind of tolerance and then maybe like clip them at that point or something.
Yeah, it's a good question. I really don't know. I know that when they talk about choosing their collocation points, they choose fewer points near the poles.
Yes, maybe that's a strategy that they never go too close to the pole, and then the physical dynamics are enough to ensure that there are not too high errors at the poles.
Yeah, it's interesting because then somehow they're able to get a nice continuous solution. Maybe it's not perfectly accurate in terms of the PDE, but at least it's continuous because you're learning a function of 3 dimensions in x, y, z in time. So maybe actually the result we see in the next slide where we pass over the poles, maybe it's actually looking better than it really is. If we're not actually training there, we may not be getting a correct solution. But at least it doesn't blow up. I guess it's a good question. I don't know.
Yeah, maybe also because it's kind of a constant advection. So maybe it's the network just picks up on the dynamics and then somehow guesses very well that it's going to sort of like go the same way because it just has to
that's true. It's basically learning to rotate the sphere, huh? Yeah. Okay. Great. Yeah, so this does seem to be a common theme with these pins, is that the way you fit them in terms of the optimization, these guys are using Atom, other people use LBFGS, and then the number of collocation points, the number of training steps, this idea of splitting it into temporal domains. I think there's another paper from the Helmholtz-AI guys in Dresden who split it into spatial domains. There's a lot of tricks you have to do.
Yes, I think so too. There's always some simplification of the problem and some ways to go around the complications of the problem. So this might be very difficult if you actually have much more complex dynamics. Also, especially small scale dynamics or very high frequent things. Because there was also this paper saying that there's this spectral bias for physics informed neural networks where they can't approximate very high frequency functions. So I think if you then have a real feel of the whole system state of a climate model or something like that, or a weather model, you might encounter problems because of that, because you actually have fast waves like sound waves. So you'd also have to somewhat ensure that you filter the higher wave modes and things like that.
Right.
I mean, if I may quickly chime in on that one, that's also a question of the type of model which you're using to represent the solution, right? There are some advances in this field. I think this is called deep neural or implicit neural representations, where you just learn different architectures for these functions for U and V. And there was this quite impactful paper a year ago, I think, called Siren, where you have cosine and sine activation functions. So I guess it really depends, especially with this frequency bias. It really depends what kind of architecture you're using. And an 8-layer, 18 hidden unit neural network might not be able to able to capture every possible kind of solution, right?
Yeah, so how would the velocities be represented there? I didn't quite get that far.
So what I'm trying to allude to is if you were, for instance, I don't know, trying to capture solutions from a couple of data points with, say, a Gaussian process, you would very carefully choose the kernel that you're using for that. You would just look at the function, and if it looks very discontinuous, you might go with one type of kernel. If it looks very smooth, you'd use a similar one. And neural networks themselves, they have just a typical set of functions which they represent naturally. If you just randomly sample the weights and you just look at the output, if you use ReLUs, you're going to get something that's piecewise linear. So over short segments, it's going to be very smooth. It's lines, and then you have these discontinuities and the derivatives. And if you use different activations functions like cosines and sines, different architectures, you're going to get different typical functions that these kind of networks will learn, and maybe if you have issues like learning high frequencies, then maybe the architectures of neural networks that you're using aren't really optimal yet.
Yes, that's a good point. Also, because it needs to be differentiable, it's also limited to fewer functions, right? If you say that some have discontinuities, they are probably not eligible for this.
Yeah, twice differentiable, and the second derivative shouldn't be zero everywhere. So values are definitely out. Okay. Any more questions? We've covered a lot of ground. Something from the earth science side, maybe.
Maybe one question that came up, I think, in our pre-discussions is, so in this paper, when they evaluated the results, they usually looked at they did look at intermediate states, but they usually compared like the final state after a certain amount of time, like 5 days, with what they're supposed to get from some reference solution. What is interesting, however, with pins is that they're not really aware of this, that we might be interested in the error of the final state at the final time, because they're just trained globally, right? You minimize some deviation from the physics and the initial states and the boundary conditions globally, essentially for all the time points equally. And they're not like numerical solvers, which have all this theory about how the error accumulates and how it grows over time, and you want to minimize this error growth. So this may be something to think about and just very broadly discuss what this means in terms of pins. Like if you could, for instance, give more weight to violations of, say, boundary conditions at later time points, or if there is even any meaningful concept for this. Because for pins, you're optimizing the whole solution at once. And it's very unclear where, at least to me, where it actually is allowed and where in practice it does make its error. So one thing, for instance, in pins, at least conceptually to me, it could occur that at some point you have some very strong discontinuity in the solutions, and before and after, it might actually then again very pitch perfectly correspond to the actual dynamics that you have, but the pins loss might be very small and everything looks nice on the pins loss. But if you actually compare the solution after time, because of this discontinuity, after this point in time where this happens, everything is completely off. But again, on a pins loss, which kind of tries to balance these different terms and is overall happy when all of them, the sum of all of them is happy, is very small, you're kind of fine. So there is it's very hard to define a type of criterion for staying true to ground truth over a long point in time. I don't know if others have ideas or something like that regarding to this, but I would be just interested in if there's any notion one could have for saying, I want a small as possible accumulation of error over time, which is what the authors seem to really be after.
Yeah, I think what they argue, so first I would also say it's very counterintuitive to have some continuous method that has the whole time domain. You could pick errors everywhere, and then you really just sample at the end. That first doesn't seem very intuitive. I think the way they argue is that if at some point the solution would be incorrect, or you have something like this, we have discontinuity, and then your gradients afterwards would still be very close to correct, then you get errors somewhere else, right? So I think as soon as you have some error in the domain, it will also become much worse afterwards, I think, right?
I'm not sure I agree. I think that if you have a discontinuity, you'll only have an increase in the PDE loss right at the discontinuity. Everywhere else, it seems to be pretty fine. I mean, I guess if you only had one discontinuity and then everywhere else it was correct, then it couldn't get the final result correctly. But if you had multiple discontinuities, it could do anything in between, basically.
Yeah, okay, my argument was boundary conditions, but in this case they are not really an argument, so yeah, I guess in this case there could be some discontinuity, but the chance could be relatively low.
Yeah, the question is are you going to find that discontinuity with your collocation points? You might not. I think you can imagine doing some interesting things to find these cases, like maybe if you solve for the streamlines, or if you solve along streamlines with a numerical solver, you should find these discontinuities. You could maybe even do something adversarial, like look for the point where the PDE is most violated. But it doesn't seem to be that these networks get very good low error and then still give the wrong answer. It rather seems to be difficult to train them and reduce their error.
Yes, I think so.
Yeah, it'd be cool also to see where they can take this in terms of, I mean, the Shuttlewater equation is extremely important for a lot of applications, but they've gone with a very simple form of it. I mean, they've done spherical coordinates, which is neat, but there's no viscosity, there's no bottom drag, there's very simple or flat bottom profiles. So it'd be interesting to see what these pins can do as we go to more sort of realistic scenarios. So I guess we'll have to see. Okay, if there's no more questions, I think we can wrap up. This was I think we covered a lot of ground in this seminar. We only went about an hour, but we really, I think, covered the topic super well. If you have suggestions for another topic, if you'd like to present, or if you'd just like to make an announcement or show your own work for 5 minutes, just get in touch. Otherwise, we will be back with you in 2 weeks for episode 28. Thanks a lot, everyone.